In this section, we want to do some explicit computations using determinants. So the idea is now that several of the computational problems we tackled in the previous chapter can be done also in terms of determinants. Namely, first we will see that under some certain conditions we can find solutions of systems of linear equations using determinants of matrices for some particular circumstances where this then gets simpler than doing the Gauss elimination method and so on. The second thing we want to do is to compute the inverse of a matrix in terms of determinants. And finally, we've seen so far the definition of the determinant, but we haven't checked yet how we can compute them. We have seen a formula for 2×2 matrices. We have seen the rule of Zarus for 3×3 matrices. But how can we go further? Like how could we determine the determinant of a 4×4 matrix, and so on and so on and so on. In general, it's quite some work as it gets bigger and bigger, but we will give you an example. I've given an example of how to compute a determinant of a 4×4 matrix by kind of reducing this to a simpler situation, as we shall see in a bit. Now, I want to begin with this systems of linear equations. Namely, in a very particular case, you can really find solutions. The next theorem is called Cramer's rule. Cramer was, I think, a Swiss mathematician. I'm not sure, but kind of the Americans will pronounce him Cramer, but since he's actually from a German country, so this would actually be Cramer. Okay, Cramer's rule. Now, assume we have the following situation. We have an invertible matrix, GLNK, and B in Kn, so some vector. Okay, let's first notation. We want to study the system of linear equations. I can already say Ax equal to B. Now this means we have n equations and n variables. So this is a situation, and also if Ax is equal to B and A is invertible, then we can just multiply by a to the minus 1 to get a solution. So this will be a case where we have one unique solution of the system. In this case, we can really compute this by determinants in the following way. Let A1 to AN now pay attention, not the row vectors, but the column vectors of A. So vertical, not horizontal, of A. Then the system of linear equations Ax equal to B has the unique solution x in coordinates x1 to xn, where xi is for every I given by det AIB, I will show you in a second what it is, divided by det A for all I in 1 to n. And now we just have a new matrix here. This matrix ABI, this is an n by n matrix, has the following columns, A1 to AI minus 1, so far the same as the matrix A. But now we do something, we take the ith column and replace it by this vector B. So we just put a B in here and leave the rest as it is. This is the matrix. So we replace the ith column by this vector B. That should be the right-hand side of the equation there. And then compute the determinant of this divided by the determinant of A. And so we can get all the solutions simply by putting replacing each column by B and then taking the determinants and doing this formula. Now this is a theorem which, like from when you first see it, it looks completely odd in my opinion, because this looks like something like why on earth should the solution look like this? Why should even this determinant play a role? And this is something where it's kind of sometimes quite hard to get the determinant intuitively, because the computational rules for determinant are sometimes not that obvious. But it turns out the proof of this is surprisingly simple. First of all, this is what I just said. Since A is invertible, the system Ax equal to B has the unique solution x is equal to a to the minus 1 times b. Now here we could do a computation of the matrix inverse, compute this and so on, but this takes some time when you really want to do this. Okay, this has this unique solution, so we already know we have a unique solution of the system. But we have to show this formula that we have. Now, viewing B as a column vector, so B in, by this I just mean I want to view this as an n by 1 matrix. So this is just how I define column vectors. Then you can see the following. Then with x written in coordinates as x1 to xn, we can just rewrite, and this is basically also how we define matrix multiplications in the end if you boil down. Ax equals b is the case if and only if the linear combination j equals 1, this is what we did in the very beginning of the chapter on matrices, I think, from sum from 1 to n, and now xj times the jth column of this. So aj is equal to b. Okay, good. So far so good. Now this is something we can do. This is ax. This is how we get it. And now this means we can use now the determinant and compute determinants of these this matrix ABI. So these ones. So namely the following. This is basically where we need the alternating property of the determinant. We compute the determinant of ABI. So this is that. First of all, we have column vectors, and the determinant we always defined using rows. Here we now use the theorem, the Posttheorem, theorem 919. No, I shifted that. The Posttheorem 917. That the determinant of a matrix is the determinant of the transpose. So ABI transpose, and now I can insert the vectors which are the row vectors of this, which are the column vectors A1 to AN, up to identifying rows, columns, and generally being a bit messy with the difference. So view them all as points in k to the n. So this means we have the determinant of A1 to AI minus 1, comma B, AI, comma, and so on to AN, AI plus 1, and so on to AN. Actually, these are row vectors, and I would need to add a little t everywhere here, but this is a bit tedious, so let me just, let me just write it like this, and insert this definition here. So this is, not this definition, this equation here. This is that of A1 to AI minus 1, and now we have the sum j from 1 to n xj, and these xj's, they are scalars, they are just numbers, times aj, ai plus 1 an. Now we can use the multilinearity of the determinant, of course, as we did before. So by the multilinearity of that multilinear, this is the same as the sum j from 1 to n, and now the xj's as the scalars can go outside. Then we have that a1 to and so on to ai minus 1, aj ai plus 1 to an. Okay? Now we can use the alternating property, because if j is not equal to I, but is inserted in here, it will also be among the others. So for any j which is not I will have this vector aj twice among the inputs, and so by the alternating property, all summands for which j is not equal to I need to vanish. So here, since that is alternating, this is the same as just the ith summand, xi times that a1 to ai minus 1 ai plus 1 an. So, and this is by construction, so the vector which has these as rows, these AIs as rows. So now we've got the right order here. But those were the columns of A, and the columns of A are the rows of the transpose. So this is the determinant of AT, and another application of Theorem 917 shows that this is indeed the determinant of, xi, forgot the xi here, sorry, xi times det AT, and this is xi times det A, and of course, so we started with det ABI, and so this is the same as this, and since the determinant of A is non-zero, since A is invertible, xi is det ABI divided by det A. And so this fancy formula gives us really, the correct result. This is Cramer's rule. So we don't need to invert a matrix explicitly, but we can just use determinants without this inversion procedure. So this is the good news, but the bad news is this is usually not that feasible, because it turns out if you, of course, what you want to do with these things is kind of make algorithms of it and put them into computers and let the computers do the work. But it turns out that for large n, so for big matrices, this is very inefficient. So for large n, Cramer's rule takes a lot, or many more computational steps than Gaussian elimination. Then Gaussian elimination. So if you really want to do a general computation for big matrices with like 10,000 columns or rows or something, we will later on, I will give you an application where there are indeed many columns, but anyway, Gaussian elimination is usually the way to go. So for small matrices, this might be faster if you want to do some fast little computation than this inversion procedure, but in general, it's not recommended to do so. Okay, now this was the first application. I'm not giving you an example of this because this is not so important at the moment, but we will now see kind of how we can, as I said, invert a matrix, compute the inverse of an invertible matrix using the determinant, and there we will also see an example later on. Or a nice consequence of this later on. I will not do all the computational steps in the following, but anyway. So, Theorem 924. So let n in n and A be an invertible matrix. No, sorry, A is just an m by n matrix. There's one consequence which also holds for non-invertible ones, which we also shall need later on. So we have some n by n matrix, then A1 to AN. These are now again the row vectors, so I'm back from columns to rows. Sorry if there's any confusion. The row vectors of A. Then A times a matrix A tilde, which I'm going to define in a second, is equal to the determinant of A times the identity matrix. So it's almost, almost the inverse, so to say. If it's invertible. So if this holds with the following matrix, where A tilde, whose entries I want to call A tilde ij, is also a quadratic matrix. And this is given as follows. So how are the entries defined? And now in a very odd way. We take A tilde ij to be the determinant of A1 to AJ minus 1. And now we insert something else here. Then we have AJ plus 1 to AN. Now, instead of the jth row, we insert the ith canonical basis vector. So here's the I. This looks really weird. And there's also, this is a theorem where I would see, if I would see this, I would notice and see it for the first time. I would say, no, there's no way this is true. This is, why should this be connected at all? And this is kind of quite a nice property of the determinant. Sometimes it looks a bit like doing magic or something, but it's really working. So given by this, for all ij in 1 to n. And now, so this is in general, so even if the determinant of A is 0, so if A is non-invertible, then we get that this product is 0. This is what's the consequence there. But the interesting case, then the invertible one, if A is invertible, this yields, so in this case the determinant is non-zero, and to get the identity on the right hand side we just have to divide by a scalar, and we get that A to the minus 1 is just 1 over det A times A tilde. If we multiply these two, if we multiply this with A, we get that we get just the identity because of this additional scalar here. So this gives the identity matrix, which is definition of the inverse. So this is a nice formula for the inverse. Oh, well, nice is relative, but anyway. But this means that we can compute these strange values here to get the inverse here. There is a more practical way of approaching this, as we will see in a bit, but let me first erase and then prove this to you. Okay, we start by making a nice observation. We take the matrix det A as a scalar times identity matrix. If we take a look at the entries of this, so what are the entries of the identity matrix? This is 1 if we have row index and column index coinciding, so if we're on the diagonal, and 0 in all other cases. And this is what we describe by the Kronecker delta. So if we want to denote the entries, this can be given as det A times delta ij. This is the ij entry of this matrix here. Okay, now, this is what we first observe. Now we do a computation where we will achieve the same result here, namely the following. So by the alternating property of the determinant we make the following observation. So recall the coordinates, the entries of this matrix A tilde were just by inserting the ith coordinate basis vector in the jth position. So here we do a similar thing. We make an observation. We take the determinant of A1 and so on, so the row vectors to Aj minus 1, and now insert the ith row again. So Ai, not Ei. Okay, so what is this? There are two possibilities. So if I is not equal to j, then we have two vectors which are, we have Ai appearing twice in these inputs, among these inputs. So then by the alternating property we will have 0. Now if I is equal to j, then these are just the rows of A, so by definition this is just a determinant of A. So this then is in short-term notation simply det A times delta ij. So this is indeed another way of writing the ij entry of this matrix here. Okay, now how does this help? So we now write the ith row now as a linear combination of the canonical basis. Here we see the canonical basis as a row vector, so we're again a bit imprecise with rows and columns. But we can then write Ai is as a linear combination, so this has the entries Ai1, Ai2, and so on. So by writing this in terms of the canonical basis vectors, this would be from the sum from 1 to n of Aik times the kth canonical basis vector, this now seen as a row vector. So what do we get? We get from this computation, we start with the right-hand side, so det A times delta ij. So this is the same as this, and now we insert this computation there. So this is det A1 to Aj minus 1, and now we have the sum k from 1 to n, Aik ek, Aj plus 1, An. Okay, and now the Aik, these are just numbers, these are scalars. So these are vectors, these are scalars, so we can use the multilinearity property of the determinant again. So that is multilinear, and simply pull these out and take the sum out. So this is the sum from 1 to n of Aik times the determinant of A1, Aj minus 1, Ek, Aj plus 1 to An. And now if we take a deep look at this, this is now a matrix coefficient of this matrix A tilde, because this is by construction Akj tilde. So this formula becomes, let's start over new, det A times delta Ij. So the Ij entry of this matrix there is the same as the sum over all k from 1 to n, Aik, and now A tilde Kj. Okay, if I had an audience, I would now ask, does this look familiar to you? This is by construction of the matrix product, and how we computed this, the Ij entry of the matrix product of this matrix A and this matrix A tilde. So this is the Ij entry of A times A tilde. So this is the Ij entry of this matrix there, so we already get our conclusion. Det A times the identity matrix is A times A tilde. So that was kind of surprisingly simple computation, I would say. For the inverse, so if A is invertible, then this means that A times, and now we can just put the scalar in here, that A times A tilde. So if we just divide everything by tilde and use that matrix products are compatible with scalar multiplications, this is then In, and this immediately implies the claim that the inverse is 1 over det A tilde. Okay, this is what we wanted to show, so this was actually surprisingly simple. Now, if we really want to compute a matrix in this way, we have to compute a lot of determinants and a lot of complicated determinants, in the sense that we have to put in all these canonical base vectors and so on and do this in a similar way. Now, the question is kind of, can we compute this A tilde Kj a bit simpler? And it turns out the answer is yes. And for this I need to introduce some new notation, and this will be, this will be fun. Maybe I'll try to get this in here. So, definition 925, at least I can start here. Okay, N is an N. A is an N by N matrix. So A is with entries Aij and N by N matrix. For two numbers I and j, between 1 and n, we let A, I, j, so as an index, the matrix I, j. This is now supposed to be an n minus 1 by n minus 1 matrix. So again, quadratic, but one bit smaller, so one column less, one row less. And this is obtained from I, and I will give you the formula in a bit, be obtained from A by deleting its jth row. So we kind of cancel the ith row completely, so we only have the other rows left, so it's n minus 1 rows, and then we do the same to its jth column. So we just pick one row and one column, so we get kind of a cross in the matrix, and just remove all the entries and put the rest together to get a new matrix. And I guess there's no way of not writing this down, so let me just give you an explicit description in terms of these entries. It's time for fast forward again, starting now. Here we go. Okay. So if you take a look at the matrix, here there's the ith row missing, and here there's the jth column missing. So we just removed all these entries and pushed the rest together. So this is how we get this kind of by canceling one row and one column of the matrix. Now, the main purpose of introducing this now is, first of all, the following lemma, and then another theorem in which way will also pop up. Now, a lemma 926. So the proof of this lemma is very technical, so this is just very tedious computation, so I will also not prove this here in class. So in the situation of the previous theorem, so in the situation of Theorem 924, so we had this matrix A tilde with these weird coefficients. It turns out of Theorem 924, it holds that the matrix entry A tilde ij of this new strange matrix, this can be described in terms of these cancelling matrices, namely this is just -1 to I plus j times the determinant of A j I. So removing the jth row and the ith column, so just the other way around. But this works, and this really, this is how we can compute this. This is a bit easier because we don't have to, so the advantage before we had the determinant of some matrix where we replaced a column by another. And here we just deleted one row and cancelled one row, so this matrix here is smaller. So actually before we needed to compute the determinant of an n by n matrix, here it's now an n-1 by an n-1 matrix. And this might sometimes make a big difference. So this is much easier to compute usually. Okay, so the proof is in the lecture notes, so let's forget about that for a moment. So I'm not giving this here. Instead, I will now use this to have a nice corollary. Namely, we'll use this to use the previous computation, so this computation of an inverse by determinants, in a special case, namely in the special case of 2 by 2 matrices. So we have a method of inverting matrices, but we haven't discussed in a special form in the special case of 2 by 2 matrices. Namely that A be a matrix, the entries, so for simplicity I call them A, B, C, and D. And that this be an invertible 2 by 2 matrix with any field. So again, this doesn't need to be real numbers or something, just field coefficients. Then the inverse, there is a nice formula for this. A inverse is just 1 over the determinant times, and now we just need to flip the entries on the diagonal, D and A, the other way around. And well, for the other two entries, we leave them almost as they are, but just equipped with a little minus sign. So flipping them and adding a sign there, and we're done. And if we want to write the determinant in terms of the entries, recall the determinant for 2 by 2 matrix is AD minus BC. So 1 over AD minus BC, D, D minus B minus C, A. So this is something you can immediately compute if you have this and compute this. This is kind of child's play. So this is just inserting the numbers there. Okay, how do we see this? This is by just applying the previous formula. Namely, so first of all, we want to apply the theorem with this matrix A tilde, and we want to compute the coefficients here like this. So what do we need? We need the matrices we obtain from A by cancelling rows and columns. Then we get a 1 by 1 matrix, which is not very exciting. So 1 row, 1 column, so it's just one element. So we compute the 4 matrices. It's almost not worth calling them matrices. So A1, 1. This would mean we take A and cancel the first row and the first column. So all that's remaining is D. So as a 1 by 1 matrix, it's just containing D. Okay, A1, 2. So we cancel the first row and the second column. So all that remains is C. A1, 3. This is, sorry, not A1, 3, A2, 1. So we cancel the second row and the first column, so we only get B. And finally, A2, 2, removing the second row and the second column, so we just get A. So this means if we take the inverse here, this is now by Theorem 924. and lemma 926. So a to the minus 1 is now 1 over the determinant of A. This is part of the theorem, and now this matrix A tilde, and by simply applying this formula, so these are the entries of the 2 by 2 matrix A tilde. So in the first one we get minus 1, so in the first one I and j are both 1, so we get 1 plus 1 times the determinant of A 1, 1. Let's maybe make this once explicitly, so this is minus 1 to the 1 plus 2. And now here we get the determinant of A2, 1. Here we get minus 1 to the 2 plus 1, and now that A1, 2. And here we get minus 1 to the 2 plus 2, that A2, 2. And now the determinant of a 1 by 1 matrix is just the entry itself. This is something I haven't proven, but this is obviously easy because if you take this permutation formula, there's no permutation but the identity if I just have one element. So there's just the one entry, which is just this number. So just by using this here, this is 1 over that A. So minus 1 to the 2, this is a plus sign, and the det of A11 is D. Not an equation here, sorry, D. So here we get minus 1 to the 3, which is minus, and the det of A12, which is C. Wait. Oh yeah, sorry. Made a stupid mistake. Sorry, almost fell into my own hole. I dug myself. So here is ij, but here's ji. This is just the other way around. So here, this is the entry 2, 1, but here the indices must then be 1, 2, and here other way around. Sorry about that. This is the entry 1, 2, and we have that of A2, 1. So here we get minus that A2, 1, which is B. Here we get minus that of A1, 2, which is C. And finally, here we have minus 1 to the power of 4, which is plus 1. And that of A2, 2 is A. And this is what we wanted to prove. So we have an explicit formula for these inverses of 2 by 2 matrix now. So this is really something that really turns out to be useful. And you can really do computations with that. OK, this is how we learn to invert matrices. So much for that. You can also really use these previous formulas to derive more formulas of inverses of matrices in other cases, but we will restrict to this simple 2 by 2 case. And finally, I will now erase and tell you how to compute determinants from smaller determinants, namely, again, by using these cancellation matrices, where we really, they're also called minors of determinant of this matrix, but by cancelling one row and one column, how can we use them? OK, let me erase. The next theorem has a name, and not only that, it is really an important theorem because you can really use this in practical computations. I've been told by a physicist that you really make use of these formulas in physics at some point, and it turns out that they are pretty useful. So let's check the following. So this is now the idea of computing determinants by determinants of smaller matrices, Theorem 928, and this theorem is called the Laplace expansion theorem. Okay, and this is now really using what we've already established, and then the proof will not be too long. Let n in n and let A be a quadratic n by n matrix. Then for all I between 1 and n, we have two methods of computing the determinant, which are part of this theorem. The first is called expansion by the ith row. Namely the following: the determinant of A is the sum of the following determinants. It's the sum k from 1 to n, and now we take minus 1 to I plus k, so some sign depending on I and k, times the entry aik, and now the determinant of this matrix aik k in which we cancelled or deleted the ith row and the kth column. So this is an n by n matrix, so this is a sum of determinants of n by n matrices. Okay, and this is expansion by the ith row, because simply what we are doing, we take, if we take I to be fixed and k going from 1 to n, this just means with a I k, these entries are wandering through the ith row. So we always take the ith row as cancelled, and now then go one by one through this and cancel the kth column for each k and do this computation there. So this I is fixed, so one row fixed, and the elements are just multiplied here in front, and then do this. And the same we can do column-wise. So B would be expansion by the ith column, and it's precisely the same, just with rows and columns in reverse. So namely, this goes as follows. The determinant of A is again a sum over k from 1 to n. Of -1 to the I plus k, so far so good. But now this I is the column index and k is the row index. So we take a k I times the determinant of a k I. Again, a smaller matrix. So again, a sum of determinants of n minus 1 by n minus 1 matrices. Here we keep, so I is now the column index, so we keep the ith column fixed, and now for each entry in the column, this is now with k going from 1 to n, we just take the ith column and go from top to bottom, and every time we delete the kth row, compute the determinant, then delete the next row, compute the determinant, and so on and so on and so on. So going through the matrix. We will see an example after the proof, and the proof is luckily quite short. Namely, it's not that much work to do. We can basically use what we did before, namely this theorem 9, so this matrix A tilde, this inverse by determinants. This is what we need here, namely the following. This theorem 924, here it is. So by theorem 924 and lemma 926, we can do the following computation. The determinant of A. So we write this now in an unnecessarily complicated way, namely as the determinant of A times delta I, where this is again this Kronecker delta, which is just 1 in this case. Now we've seen this was the entry of this matrix delta I times identity, which is in position II. We saw that this matrix, which has this entry here, coincides with the matrix A times A tilde. So the A times I tilde has in this II entry, this is the same as the sum from k equals 1 to n, aik times A tilde ki. But this is now where the lemma kicks in. By the lemma, we had a formula for this, and the formula was precisely what we need, namely this is the sum from 1 to n aik, and now this was -1 to the I plus k, and determinant of the matrix A with the cancelling, but now with indexes swapped, so aik. So, and of course, just multiplying this here to make this look nice, this is just the sum from 1 to n of -1 to the I plus k, aik times det aik, and there we already have it. This is just what we wanted to show. So this is basically just what we did. It's just not that easy to recognize that this is only the standard computation we've done already before. Okay, now for the column statement. This follows by applying part A to the transpose. Then the rows become columns and the columns become rows. So by applying A to a transpose and using that the determinant of A, using that the determinant of A is the determinant of the transpose, as we've shown. And then we just do this for, then columns become rows and we get precisely the same formula. So this already shows the claim. Okay, now I will give you one example with actual numbers. Okay, we want the determinant of the following 4x4 matrix, and I now take a real matrix. A has entries 2, 5, 1, -2, 1, 0, 3, minus 2, 4, minus 1, minus 2, minus 1, and 3, minus 5, 2, 4. So this is a real 4 by 4 matrix. Okay, I will not do the full computation, but to see what it is. So what we now want to compute is to, and I will just want to show you how the procedure works here. Now, we want to use expansion by the second row. Okay, now what does this look like? Expansion by the second row. So I'm now writing these matrices with rows and columns cancelled. I will write them down explicitly in a bit. So just first of all by Laplace, by the Laplacian theorem that we just saw, the determinant of A is now given as follows. We are deleting the second row and then go column by column and need the respective entry of the rows. So the first one is minus 1. So we would go through this row number 1. So in the first one, this is index, row index 2, column index 1. So we get minus 1 to the 2 plus 1. And now, the entry, which is just 1 in this case, times the determinant of A to 1. Okay. Next thing is minus 1 to the 2 plus 2. So this the second entry in the row. And it turns out this is good because there is a 0, so this is irrelevant here, times that A to 2. Okay, this we don't need to care any further. Third entry, this means we get minus 1, so this has row index 2, column index 3, 2 plus 3. And here we get 3 times the determinant of A to 3. And finally, we get minus 1 to the 2 plus 4. From this element, and now we get minus 2 times the determinant of A to 4. So let's clean this up a little bit. So this minus 1 to the 3 is a minus, 1 is 1, so we will get minus that A to 1. So this is 0, so we don't need to care. This is minus 1 to the 5, so it's a minus. So we get minus 3 times that A to 3. Here we have minus 1 to 6, which is plus, but here we have a minus, so this is minus 2 that A to 4. Okay, this is what we have, and now we need to compute the determinants of these matrices. And to write down these matrices once again, or once explicitly, here A to 1, so it's a 3 by 3 matrix, and it's obtained by cancelling this row here. Maybe let me, so we cancel this row, we delete this completely, and now this time we delete this column as well. So we have these, and these entries left, so 3 by 3. So the first row would be 5, 1, minus 2. Second row is then these 3 entries here, minus 1, minus 2, minus 1. And now these 3, minus 5, 2, 4. Okay, A to 2 we don't need, so we need A to 3. So we again cancel this row and this column here. So we get in the top row 2, 5, minus 2 left. 2, 5, minus 2, minus 2. So the second row doesn't exist anymore. So in the third row, if we cancel this and this, we got 4, minus 1, and minus 1 left. 4, minus 1, minus 1. And here, so cancelling this, we get 3, minus 5, and 4 left in the last row. 3, minus 5, 4. And finally, A24 is equal, so we cancel this row and this column. So here we have 2, 5, 1. Okay, second row is gone. So here we have 4, minus 1, minus 2. And finally here, 3, minus 5, 2. 3, minus 5, 2. Okay, these are now 3 by 3 matrices. And for 3 by 3 matrices, we have the rule of Sarus. And I will not do the computation in full detail because that's I think it's not necessary. This should be easy to do for you. So I just give you the results using the rule of Zarus, we get, and this is now a bit surprising maybe, the determinant of A21 is 3, the determinant of A23 is minus 79, and the determinant of A24, which is quite innocently looking, this is minus 111. So this is a good example where you see that it's really not easy to see the determinant. I mean, even if the indices look, the entries look relatively harmless, the biggest one here is 5, and minus 5 the smallest. So you think, okay, what could go wrong there? But it turns out it's really, these determinants can be very big, and you can really can't tell from a matrix just by looking at it what the determinant is. No chance. Okay, now we just need to insert these. So we get, if we put this in here, that A is minus 3 minus 3 times 79, so plus, minus, minus, and another plus, minus, minus, plus 2 times 111. So this is a big number, and this is, I checked this, 456. Okay, so this is a very big value. So again, this matrix here, which is also quite innocently looking, in that 5 and minus 5 are the biggest and the smallest entries, the determinant is insanely big compared to that. So keep in mind the determinants are really hard to estimate just from looking at a matrix. Okay, these are computations we can do. So this was reducing a 4x4 determinant to a 3x3 determinant. And of course, we could now do the same inductively. If we would have a 5x5 matrix, we could expand by some row and would get a family of determinants of 4x4 matrices. For each of these 4x4 matrices, we could do again this procedure and would get back determinants of 3x3 matrices, and so on. I mean, if I give you a 20 times 20 matrix, theoretically you could expand and expand again and again and again, and do a lot of iteration steps until you get a lot of smaller determinants that you have to compute. And, but the good news is, I mean, this is tedious to write down, but this is algorithmic. This is something you can tell a computer what to do. So do this and this and this, and so this number of steps, this could you do an algorithm, and this is how you can feed a computer to compute determinants explicitly. So yeah, this is kind of how determinants are done by, if you just have this right scheme there. So there is a really technique where you can really do this step by step, and this is what a computer can do, and so this is how computer determines this. And I hope this is insightful for you and more interesting than just putting a matrix into a computer and getting a value spit out. So now you know what the computer might be doing. Okay, so much for determinants for the moment. We'll stay in this chapter with properties of endomorphisms and next take a look at eigenvalues, which are really interesting numbers associated to endomorphisms, which tell us a lot about these endomorphisms and with which we can study them a bit more in detail and classify them a bit. See you in the next section.